requests for sharing of the books that I had sent by mail. Actually, I had mentioned earlier as well, the books have been shared with your common mail ID. So if you download from there, you will get it, because it's not possible for me to, give a sharing, sort of share with each and every student. It's going to become impossible, because so many books with so many students as well. So those of you who have not have somehow missed that, meaning that did not understand that I had asked you to do that, you can go to your common mail ID. It is shared with the common mail ID. So from there you can download directly, right? So that's one thing. The other thing is that the class test is due, I think. So basically, we would have to hold the class test very in the near future, you can say. And I propose that we have the class test next week, say, for example, on 3rd November. Is that okay with you? 3rd November, say 12 to 1, Wednesday it should be. Is it okay with you?
Ma'am, could you hold it next to next week? Then it would be best for us.
Actually, there is no end to this next to next. Okay, which, let me see the dates, just a moment. In fact, we've got a sort of list of holidays as well. Let me see that. University is closed on 10th, 11th. It is Wednesday, Thursday. Okay. But that doesn't prevent us from holding the test, does it? Say 10th is a holiday on account of Chhat Puja, it seems, as per the university notification. But is there anybody who has any objection if I hold the class test on 10th November, Wednesday in the morning, say 12 to
Ma'am,
1?
ma'am, for
Yes.
some students, it might not be possible.
Then when
Ma'am,
do
for
you
some,
propose? I understand. Then when should I hold? Okay, then 9th November. 9th November is Tuesday, say in the evening from 5 to 6.
ma'am, you can take the class on 9th of November. Class test on.
Not class test, I'm saying.
Yes, ma'am, class test.
9th of November from 5 to 6. Okay.
Yes,
So basically, it is going to be again online, and I'll be sending the question paper to the two common mail IDs, but each one has to submit from their individual mail ID. So you download the question paper, and um, it will be given to you by 5 p.m. You have to submit by 6 p.m. I'll give you another 15 minutes, say. So by 6:30, all the answer script should be with me. Okay, so I'll write that and also send to your common mail ID, so that nobody misses out on what I've said, I mean verbally, but tentatively meaning that it's fixed on that day, though I'll give you in as an email. Okay, so let me just put that on record. It is 9th November 5 to 6. I'll just write that somewhere.
Ma'am, what will be the syllabus of the class test?
I'll tell you, just wait, let me note
Okay.
down. Okay, so syllabus actually will be till the end of what I teach today. That would be the time response for first and second order systems included, and if whatever I complete today. Um, right, and as usual meaning, of course, you are not used to my way of questioning. the question paper, the class test will consist of both theoretical as well as problems, numericals as well, right? So you would have to solve all questions would be compulsory. You would have to write it and submit it. Write it on plain paper. Write your name, roll number as well on the answer script, and then submit. I'll give you the format of the file name and all that. So file name should consist of your roll number and your name, and then of course the subject. So I'll give that format in your mail, maybe today or tomorrow, or at least by Saturday it should be there with you. The syllabus will consist of whatever I complete today in today's class, right? So now I'll just go to the class itself. I'll share my screen. Right, so is the slide visible? Can you see the slide?
Yes,
Yes,
ma'am.
ma'am.
Right. So if you recollect in the A section, I had actually, I mean, started off with this time response for the system model, whereas the B sections did not attend the class. So they have missed that, but I'll be continuing from where we left off for the A section. So, I mean, I'll just do a very quick recap, maybe 3-4 minutes of what we had covered, so that the others also know that that portion has been already done. It's going to be taken as done. So time response for the system model, you would recollect, we had spoken about the natural response and the forced response, and then for the definition of poles and zeros, concept of cancelled poles, cancelled zeros. Then for the first order and for the first order system as well as for the second order system, we had seen the general, expressions for the time response, and then we had also spoken of which portion of the transfer function accounts for what part of the response, time response. So basically, and we had spoken about what would happen if poles or zeros were shifted to the left or to the right. Left or right meaning away from the imaginary axis or towards the imaginary axis. So these were done, and then of course that is the definitions which you are already aware of in your second years you had studied. They were recapitulated. And then similarly for a second order system as well, we had seen for the different cases of underdamped, undamped, critically damped, overdamped, uh, what happens to the response, that is the expression for the response as well as the nature of the response. So now actually I think I had also shown you this slide, but I'll start from here today. Here we find that this is the general response for a second order underdamped system, right? And over here you find two things. Two things in the sense that you find that this is the plot, the pink one over here, right? And the plot is oscillatory in nature, meaning it's sinusoidal in nature. However, the sinusoids are not of fixed amplitude. So the amplitude of the sinusoid is decaying like this and is decaying within an envelope, an exponential envelope to be very specific. You would recollect that basically this envelope depends on the term that is exponential, that is e to the power of minus at, and that value of a over there is responsible for how slow or how fast this envelope decays. So how fast it decays means, say for example, if the value of a is large, you would have a fast decaying envelope, in which case the sinusoids would be damping out very fast before, say in 1 or 2 cycles like that. That's a general thing I've spoken of, but rather that's a specific thing I've spoken of, but there will be, the decay will be very fast. On the other hand, if the value of a, that is I think I've said just the opposite, isn't it? The value of a is small in that case, basically, it is going to take a long time. It's going to take a long time to decay. That means that the envelope is going to be, such that it's going to be slow. That means the sinusoids are going to be decaying slower compared to if the envelope was such that the convergence was fast. So that actually corresponded to the general, if you recollect, I'll just go back to slides. The general expression over here, you see the sinusoidal term. This is the A or alpha, whatever you call, this is the term that I'm speaking of, right? So the value over here will dictate how fast or how slow this envelope decays. So the general response is shown over here. You can see the exponential decay is generated by the real part of the complex pole pair. We had spoken of that, and we've also spoken about the fact that this sinusoidal quantity, or the oscillation that you see over here, has a frequency. Now, the sinusoidal oscillation, the frequency is going to be dependent on the imaginary part of the complex pole pair. So basically, if you have the value of the imaginary part as large, the frequency will be large, meaning that there will be many more oscillations within this. That is, the frequency of oscillation will be more, whereas if the imaginary part is small, the frequency of oscillation will be small. So the same figure on the right hand side, but now we actually again define two terms which you are again familiar with. One is known as the natural frequency of oscillation, that is omega n. So it is defined as the frequency of oscillation of a system without damping. So if the damping were not there, the frequency at which the oscillation would have taken place is denoted as omega n and is known as the natural frequency of oscillation, right? Another term that we would have to be familiar with is known as the damping ratio, again something that you're familiar with, though of course what I'm going to state next you may not be familiar with. So damping ratio is basically, it's denoted as zeta, and it is the ratio of the exponential decay frequency to the natural frequency in radians per second. So if I express that instead of natural frequency, if I express it in the terms of natural frequency, or for that matter, instead of the frequency, if I express it in terms of the time, that is the period of oscillation, then it's going to boil down to 1 by 2 pi into natural period by exponential time constant. So basically, because the unit over here in the denominator is the radians per second, this 2 pi is going to come over there. Now, I had an animation over here, but for that again I would have to exit and share the whole screen. Okay, I'll do that because not too many people are left to come, but otherwise what will happen is I'll just stop the sharing for a moment and then share my whole screen so that I can show you the animation. Still people are turning up. Oh, the animation is still not working, maybe because of my bandwidth. Anyway, so what we had over there is, okay, in that case, I'll just stop sharing. Escape, and then present the window itself. I'll just verbally tell you what I wanted to show. It's not working. Right, so I hope it's visible again. So here now, what I have is, there you can see three masses. One is the red one, the green one, and the blue one. And on top, there are three terms which are written: overdamped, critically damped, and underdamped. What the animation would have showed you if it were visible is that in the overdamped case, this mass, say for example, if it is subject to a force, if say I apply a force such that it is pulled down and then left, you would find that because it is the overdamped case, it would actually gradually go back to the original position and stay over there, right? In the critically damped case, it would still, again, I mean, if I apply the same force over here and pull it down, then it is going to go back to its original position without any oscillation. But if you compare the response of the overdamped and critically damped, you would see that the overdamped case, the response is slower. It's going to take more time to go back to its original position compared to the critically damped case, right? On the other hand, in the underdamped case, if I apply a force and take it down, I mean pull it down and then leave it, you're going to see that there will be, the mass will be oscillating up and down, and the oscillations will gradually be damped out. Damped out meaning that the amplitude will gradually decrease until it reaches its steady state value, right? So that is what I actually wanted to show, but I mean the animation is not working anyway. So physically, the damping ratio is what makes it go back to its original position. You can, I mean, come to know about how many oscillations there are going to be before it goes to its steady state value, or how fast or how slow it reaches the steady state value for the three cases of overdamped, critically damped, and underdamped. Over here as well, basically, the two masses would have shown a plot over here for the undamped and underdamped cases. Undamped, can anybody tell me what will be the nature of the oscillations if, say, the black mass is for an undamped system? What will be the nature of oscillations if I plot it versus time? What would
it will oscillate about a steady state. It will not come in steady state.
But the amplitude of oscillations will remain constant if it is undamped. Okay. Undamped means it's going to keep on oscillating between two, I mean, upper and lower amplitude values, but it is never going to die down. The oscillations are going to remain constant in amplitude. On the other hand, for the underdamped case, you would find that the oscillations, yes, it would start off, I mean, again, in a similar fashion, but the amplitude of oscillation would be such that there would be a steady decay before it goes to its steady state value, whatever be the steady state value, depending on the force I have applied. So basically, those are the two cases that would have been shown. So now we come to the physical significance of damping ratio. So as far as damping ratio is concerned, damping ratio is a dimensionless measure describing how the oscillations decay after a disturbance. Disturbance includes, say, a forcing function, meaning that if I apply a force, or that's in the mechanical system. In an electrical system, the equivalent would be if I apply a voltage source, right? So anyway, so after a disturbance or a forcing function is applied, how the oscillations decay, that is what the damping ratio shows, or I mean, that the damping ratio is the factor on which such oscillations, the decay of such oscillations depend. And the damping ratio is dimensionless. Now, when I say that, I mean something. So over here, you can see on the diagram an underdamped response over here. Now, what I mean by the fact that the damping ratio is dimensionless means that you have on this side the time axis, right? And the other side is the amplitude axis that's marked over here. So amplitude is CT, and the amplitude unit would be appropriate. I mean, say for example, if it's a mechanical system, it may be position. If it's an electrical system, it may be a voltage, and so on, whatever. So now the other axis, that is this x-axis over here, you find is time. Now, time over here, of course, I've put time in seconds for this particular plot over here. But now, I mean, what I mean by saying that the damping ratio is dimensionless means that here, this axis maybe having any units meaning that, say for example, if the damping ratio is say 0.7, so that is a ratio, right? So now if I see the plot over here, if I plot it versus say time in seconds, and this is the amplitude, and I see that it is basically for a particular system, I have say 1, 2, 3, 4, 5 or something oscillations. Now, if for a second system again, I have the same damping ratio, I would see that irrespective of what the time axis is over here, the number of oscillations before the response decays would be remaining the same. What I mean is that, say for example, for system 2, I have the time over here marked in milliseconds, and it has say 1, 2, 3, 4, and 5 oscillations before it decays. That would be valid for the same damping ratio. So how many oscillations before it decays is what is indicated by the value of the damping ratio, which is independent of the time axis. Time axis meaning the unit of the time axis is not of interest over here, right? So basically, the damping ratio is a measure of describing how rapidly the oscillations decay from one cycle to the next. So this is important, from one cycle to the next. It's not indicating, I mean, how rapidly it rapidly rather does not refer to time over here. Okay, so it indicates that, say, I mean, from one cycle to the next cycle, how much of decay has taken place. That is what would be indicated by the damping ratio, irrespective of what you have, the scale that you have on this side. The damping ratio is convenient in describing common aspects of behavior, as it is a normalized or non-dimensionalized approach, right? So the damping ratio is essentially dimensionless, and I mean irrespective of what you have at the scale of the time axis over here, how much it oscillates, how many oscillations take place before it reaches a steady state, is what is indicated by the damping ratio. Right. Continuation of that is that the damping ratio is a quantity that compares the exponential decay frequency of the envelope to the natural frequency of oscillation. So exponential decay frequency refers to the envelope over here, how fast or slow it decays, and the natural frequency means the frequency of oscillation over here. The ratio of these two is what the damping ratio is. This ratio is constant regardless of the time scale of the response. So whether you have this scale as seconds or milliseconds, or I mean for that matter in hours, whatever it is, the same damping ratio would give you a similar sort of plot, meaning visually it would be the same if it has the same damping ratio, because damping ratio is a ratio and irrespective, it's not dependent on the time axis, time scale, I mean. The reciprocal of the damping ratio, which is proportional to the ratio of the natural period to the exponential time constant, also remains the same regardless of the time base. Naturally, if your damping ratio is not dependent on the time base, naturally the reciprocal also is not going to be dependent on the time base. Now over here on the right hand side, you find something is written that, for example, a system whose transient response goes through 3 cycles in a millisecond before reaching the steady state would have the same measure or same damping ratio as a system that goes through 3 cycles in a microsecond before reaching the steady state, right? So what is being said over here is that if the system goes through 3 cycles before reaching the steady state, whether the time base is in microseconds or milliseconds or seconds, all such systems would be having the same damping ratio. Now, a numerical sort of example, just to give you a feel of, how that is actually happening. So, proof of the pudding means basically the fact that damping ratio is what dictates how many cycles are going to occur. That is what we are going to see over here. So, here, say you have system 1, system 2, and system 3. 3 systems are shown over here, transfer functions are shown. S square plus 2 into 0.1 into 2s plus 4. Why it's broken up, you can understand, isn't it? This is omega n squared, so 2 square over here, and then you have 2 zeta omega n s. So omega n is 2, and then the damping ratio is 0.1 for this first system. For the second system, you have the natural frequency as omega n equal to 3. So 3 square by, you can see, s square plus 2 zeta into 3s plus 3 square. So basically over here as well, though the omega n value is different from the first system, damping ratio is the same as the first one, right? Similarly, the third system, where you have 10 square by s square plus 2 into 0.1 into 10s plus 10 square. So omega n is 10 over here, whereas damping ratio is 0.1. So now actually the response to a unit step input for all the three systems have been separately plotted and are shown. The results are before you, you can see. So you see that though the natural frequency of the three systems are different, because of the damping ratio, basically, you find that because of this, because the three systems have the same damping ratio, you find that the number of oscillations before they reach steady state is the same. So here you can see, just visually, I'm trying to, give you an explanation over here. You can, of course, do the plot and see for yourselves. So you can see 1, 2, 3, 4, 5, 6, something like that, a few more over here. So similarly, 1, 2, 3, 4, 5, 6, and a few more smaller ones, very small, just around the steady state. Similarly, for this one, it's 1, 2, 3, 4, 5, 6, right? So you see that it is another thing that you can see is that the time axis also has been, marked in the three cases. Here you find that this, the steady state is reached within, say, around 30 seconds, whereas this one is reached around 20 seconds, whereas this one is reached around 6 seconds. So because the natural frequency of oscillation is different, naturally the time period of oscillation, the damped time period, is different for all the three cases. However, for that reason, basically, the time scale has to be different in the three cases. On the other hand, because the damping ratio is the same in the three cases, if somebody just sort of erases out this portion, you would apparently find that the three responses are very, very similar, arising out of the same damping ratio. Because the three systems have the same damping ratio, you find that number of oscillations before they get damped out or reach the steady state are the same in the three cases, right? This is going to give you a feel about, the significance of the damping ratio and the fact that it is actually a ratio and not dependent on the time scale. Now, okay, so number of oscillations, the same thing is shown over here. Number of oscillations before attaining steady state is same irrespective of the time scale, as the damping ratio is the same in the three cases, right? On the other hand, now, here we have a sort of the opposite counter, not counter example exactly, but here in this system, for the same system, for different damping ratios, the responses have been shown. So same system means we have omega n square, which is 3 square by s square plus 2 into 3, that is 6 into zeta into s. So 2 omega n into zeta s plus omega n square. So in this case now, the zeta is being varied, and for different zeta values, the responses are shown over here. You can just see, to get an idea about how it's happening. When the value of zeta is 0.05, you find that this is the response, whereas when it increases, damping ratio increases, this is the response. This is for 0.1. For 0.2, you can see the response. For 0.5, you can see the response. 0.7, again, you can see the response. So basically, you find that for increase in the damping ratio, the number of oscillations before the steady state is reached is going to decrease for the same omega n value. So now, again, coming to some definitions, the system specifications for a second order system. Again, something you are familiar with. We are just going to restate those simply because, as I mentioned in the previous class, you would be requiring these for other numerical problems as well as for, whenever you want to work with a control system, you would be requiring these definitions. So naturally, I have restated them over here. So let the general expression for the transfer function be gs equal to b by s square plus as plus b. So without damping, the poles would be on the imaginary axis and the response would be undamped sinusoid, right? So it would be an undamped sinusoid when a is equal to 0. We've already done that earlier, just to recap, right? So purely imaginary poles, a equal to 0, and the transfer function is given over here. Now, by definition, omega n is the frequency of oscillation of the system when the damping ratio is equal to 0. So, frequency of oscillation of this system is essentially omega n. So, basically omega n will be your dependent on root b, right? So, since the poles of this system are on the j omega axis at plus minus j root b, omega n is equal to root over of b, because omega your b is equal to omega n square. So over here you have omega n square by s square plus omega n square. Naturally omega n is equal to root b. Now assuming an underdamped system, so that was for an undamped system when damping ratio is equal to 0. For an underdamped system, complex poles have a real part equal to minus a by 2. Right, so this is the transfer function that we are speaking of. So if you have, I mean, the if you break it up into the complex poles, you would find that the complex poles would be at minus a by 2 plus minus j root beta root b. So over here the real part is at minus a by 2. So the magnitude of this value is the exponential decay frequency, right? So that actually leads to this, that is zeta is equal to the exponential decay frequency by the natural frequency in radians per second. So exponential decay frequency is a by 2 by natural frequency in radians per second is omega n. So basically a by 2 whole by omega n is equal to zeta, which gives us this, that is a is equal to 2 zeta omega n. Anyway, I mean, from this transfer function as well, comparing the coefficient with the standard form, a is equal to 2 zeta omega n, that is understood, and that is what we have seen here as well. So here, this is a sort of summarization of whatever we've done. So undamped case, you can see the pole pair is on the imaginary axis, and in the underdamped case, complex conjugate pole pairs both in the left half of the S-plane if it's a stable system. And you can also see the imaginary part value plus minus j omega n root over of 1 minus zeta square, which we also call as omega d. Omega n root over of 1 minus zeta square is the damped frequency, that is omega d. Similarly, for a critically damped case, we've already seen that the pole pair is coincident, meaning they are at the same location on the real axis, and that the value of the real pole pair is equal to minus zeta omega n, right? And the overdamped case, in which case basically again the poles are both on the negative real axis, but they are not coincident, they are placed at different locations, and these can be seen to be, as you can see over here. So basically in the overdamped case, again if you factorize, you would be able to see these values. So now the parameters associated with the second order underdamped system, you would see that this portion is somewhat an overlap, a bit of repetitive in nature, but I mean, since these are very, very important, it's been stated over and over again, after which we'll go to the next module, which is different. So if the your transfer function is given by a standard second order system, that is omega n square by s square plus 2 zeta omega n s plus omega n square, and for a unit step input, the response, that is Cs, will be equal to the transfer function into 1 by s. So that 1 by s you can see over here. And taking the Laplace inverse, of course, breaking up into partial fractions and all that, the steps are there. And taking the Laplace inverse, the time response can be obtained as this. So this is the general time response, where phi is again this, right? These we've already seen, but it's given again. So now coming to the definition for the peak time. So peak time is given by, rather it is defined as the time required to reach the first or maximum peak overshoot. That is basically if you have a response which is shown over here, something like this, then the first peak is this one. So the time to reach the first peak is going to give you the peak time, right? And it can be calculated and seen, and the expression can be found out. So after finding out the expression, basically the final expression boils down to this, that is Tp is equal to pi by omega n root over of 1 minus zeta square, or also written as pi by omega d, where omega d is the damped natural frequency and is equal to omega n root over of 1 minus zeta square. That was something you already knew, I guess. This as well, partially at least you know. So now the percentage overshoot, denoted as percent OS like this, is the amount that the waveform overshoots the steady state or final value at peak time. So basically this is the steady state value you can see. Now the amount by which the first peak actually overshoots the steady state value is known as the percent overshoot. The expression for the percentage overshoot is found over here, from which now taking log, I mean natural log on both sides, etc., etc., a value for, an expression for the damping ratio in terms of the percent overshoot has also been found out. Now, why has this been found out? You would find that mostly this expression is, usually it's not used, but it is very useful when you are doing experiments. Say, for example, you have a second order system and you have somehow, sort of excited it and got the response, right? So experimentally, you have obtained a response, but you don't know the damping ratio. So to back calculate the damping ratio, you can always find out the percent overshoot over here and then plug it back into this expression, which is going to give you the value of the damping ratio. So that is why, this expression could be used for experimental purposes, right? So, on the other hand, of course, if you know the damping ratio, the percent overshoot can already be, always be found out, and it's given over here. So this expression, essentially, you need to know. It has to be handy. You will require it off and on. Next, we come to the settling time. So the amount of time required for the damped oscillation of the transient response to remain within plus minus 2% of the steady state value. That is known as the settling time. Alternatively, in some cases, plus minus 5% may be taken. So what it means is that you find that the response is oscillatory and then reaches, at least approaches the steady state value. So, the time taken to reach exactly the steady state value may be very, very large, but you would find that often the responses would be sort of coming close to the steady state value and oscillating very near to the steady state value. So that is why now the settling time has been defined as not the time to reach the steady state value, but to stay within some percentage of the steady state value. So there are two alternative, sort of schools of thought. One which takes plus minus 2% of the steady state value, for which the expression is given over here. If you take plus minus 5%, again, there would be an alternative, expression for that. You would find that in standard textbooks. So now the settling time when plus minus 2% is criterion is taken is given by 4 by zeta omega n, or it's also written as 4 by sigma d, where you can see the zeta omega n is actually the real part of the complex conjugate pole, right? So basically the magnitude, so that is denoted as sigma d, which is the real part of the pole, right? And it's the exponential damping frequency. So zeta omega n is also the exponential damping frequency because it is the real part of the pole, and we said that the exponential damping frequency is equal to the real part of the pole. So that is the settling time. Now the rise time, again a term which you're familiar with, right? The time required for the waveform to go from 10% to 90% of the final value, or you can say 0.1 to 0.9 of the final value. So basically that, over here you can see that that can be found out, right? Again, expression you would find in standard books. So now this is a general sort of representation of the underdamped second order system case, which we've already done, but again, I mean, just I'm showing. So if the plot is done in the S-plane, you find that this is the real, real axis, and this is the imaginary axis. The real part of a complex conjugate pole pair, because we are considering the underdamped case, it's a complex conjugate pole pair, and for that matter, complex conjugate pole pair on the left half of the S-plane. So the crosses indicate the pole pair, which are complex conjugate in nature. The real part of the pole pair is given by minus zeta omega n, which is also denoted minus sigma d. That's the real part. And the imaginary part is given over here as, you can see, j omega n root over of 1 minus zeta square plus minus, right? So basically, that is the real part. So now, I mean, the significance of the damping ratio as per this particular plot, you can see that is this angle over here, the cos inverse of this is going to, cos inverse of the damping ratio is going to give you the angle theta over here. So basically, depending on the damping ratio, this angle is going to be varying, right? So cos theta, cos of this angle is the damping ratio. Naturally, from geometry, you can understand why it's written that way. So now we come to something else, that is the effect of adding poles and zeros to a transfer function. So basically, I mean, till now we have just done the standard definitions and the second order response, and in the last class we had done the first order response. So now we are going to proceed a bit more, starting from that point onward, which is the effect of adding poles and zeros to a transfer function. What we mean over here is that often while designing, what is done is that a very sort of simplistic model is first sort of designed, it is assumed, and then the design is done on the basis of that. Then we try to find out what will happen if another pole is added or another zero is added. So that way, basically, the model that you start off with, you build up on that, and then make appropriate corrections and see whether that is going to suit your specifications or not. So what I mean to say is that the general approach to design is not, designing a very complicated system all at one go. It is going to be a very costly affair, and it's also going to take a lot of, it's going to create a lot of complexities, and as a result of which it's going to be not cost effective, in the sense that once you go wrong, you would have to redesign the whole thing again. So what is done is a starting point with a small order system is designed first, and then the effect of adding poles and zeros would be actually then visualized, and appropriately the designer proceeds in that way. So now we are going to study the effect of adding poles and zeros to the transfer function. So successful design of control system cannot depend solely on choosing the values of the system parameters so that the characteristic equation roots are properly placed, meaning that the pole placement is of course essential for successful design, but now the zeros of the transfer function are also important in determining the transient response and stability of the system. So what the summary of this slide is that for any successful design, both the poles as well as the zeros are to be placed at appropriate locations so that your system can meet the required specifications. So now we are going to study what happens if poles are added to the open loop transfer function of a system. So what you find over here is that basically the open loop transfer function for a second order system is first considered. So that is given by omega n square by s square plus 2 zeta omega n s, right? So if can you understand why I said this? Because if your open loop transfer function is GS, and if I ask you the closed loop transfer function for a unity feedback system will be, you can see it's written over here, GS by 1 plus GS. So when you do that, if your GS was equal to omega n square by s square plus 2 zeta omega n s, only this first two expressions over here, not the last one. So now if that is your GS, then your closed loop transfer function will be what? It's going to be omega n square by s square plus 2 zeta omega n s plus omega n square. So basically for a standard second order system, the open loop transfer function is given by this. When you close the loop, it's going to give you your second order closed loop transfer function. Now what is done over here is that one pole has been added to the open loop transfer function. So when I say that, the pole you can see is added over here at a value, or the location of the pole is at minus 1 by dp, isn't it? Because here you can see it's in the time constant form and the term shows you 1 plus dps, right? So now if I were to find out the effect of the addition of pole to the one pole to the open loop transfer function, what I would have to do is I would first of all have to find out the closed loop transfer function. So that is done first. So the closed loop transfer function given by GS by 1 plus GS, because we are assuming a unity feedback system. So once you take this GS and then calculate all that, this is what would be resulting, right? So GS by 1 plus GS from this GS, if you calculate, is going to be given by this. So what do you find over here now with respect to the original system now? Original, give me a moment. I don't know whether I'll be able to. I'll just. Yeah. What was the original closed loop transfer function without the pole? What was the closed loop transfer function? Can anybody tell me? When the pole was not added, what was the closed loop transfer function for this?
Omega n square by s square plus 2 zeta omega n x plus omega n square.
Exactly, good. So that was the original closed loop transfer function, omega n square by s square plus 2 zeta omega n s plus omega n square, right? Now, because a pole has been added to the open loop transfer function, the closed loop transfer function has now become this. So comparing this with the original second order transfer function, that is original meaning without the addition of the pole, we would conclude certain things. So first of all, I mean, the plots have been shown over here on the right hand side for specific values of zeta and omega n. So omega n considered as 1 without any loss of generality, just for the plot some values had to be considered. So that has been done. And over here now, the case of zeta is equal to 1 has been taken. So zeta equal to 1 means what? What is the damping like? It is going to be a critically damped system. So the response would be critically damped if the pole were not added. So basically for TP equal to 0 means what? TP equal to 0 means here this is 0. So the original second order system is what we had. So that response is shown by the blue plot over here. And you can see that it is a critically damped system response, right? Now, when the pole is added and successively the value of TP is changed, first TP is taken as 1, and for that the plot has been done by using MATLAB. You can see the response anyway. And for a TP value equal to 5, again, the plot has been done by using MATLAB. So now the effect of a critically damped response has now become a peaky response, right? And successively by increasing the TP value, the peak is increasing. So basically the system response, first of all, the overshoot has changed, overshoot has increased. Also, the response has become more oscillatory, right? So this is actually a general sort of effect that will occur when one pole is added to the open loop transfer function for a second order system. So the system response becomes more oscillatory and may even become unstable. So basically, I mean, you can see it's becoming more and more oscillatory. So a larger TP value would make it, I mean, oscillate, it would make the oscillation even larger, and in a case may come when the system becomes unstable. At least it becomes less stable, that much we can understand, because a response which is more oscillatory is obviously less stable. Also, what we observe is that there is an increase in the rise time of the step response. So basically, for the blue response, you find that the response is sharp, meaning faster. So rise time means the time taken to reach from 10% to 90% of the steady state value. So over here now, you would find that the rise time, this red one at least, you would find that the rise time has definitely, increased. So that is again a general effect of the addition of one pole to the open loop transfer function. A third effect that we would be observing, I have another plot on the next slide, but I'll read this before going to that plot, is that when a pole is added to the open loop transfer function, it reduces the bandwidth of the system, thus cutting out high frequency components of the output signal. So basically, the bandwidth is reduced. So for that, we would have to go to the closed loop frequency response, which the plot of which I have on the next page, that is this one. So now over here, you find three cases have been plotted. Three cases meaning here it's shown the TP equal to 0 case is the blue one, so the first one, and the green one meaning TP equal to 1, that is this one, and the red one is TP equal to 5, so that is this. The frequency responses are also color coded in the same manner as the time responses, so you can understand. Sorry. Now, speaking of bandwidth, how do we know how much the bandwidth is? First of all, one thing that I would like to mention is that the responses that you find over here, the frequency responses that you find over here, apparently look like the magnitude of the Bode plot that you are familiar with, but they are not so. What it is that it is the closed loop frequency response, meaning the magnitude of the closed loop transfer function versus frequency is plotted, right? So that is the, from there we would be able to see whether the bandwidth increases or decreases. But before that, let me ask you whether you are familiar with what bandwidth is. What is bandwidth? It's of course written over there, you can see, but anyway, any idea?
Yes, ma'am, we studied it in filters.
That is why I'm asking, yes. So you've studied it in filters. So here it is restated, you can see. The bandwidth is the frequency at which the magnitude of the closed loop frequency response drops to 70.7% or 3 dB down from its zero frequency value. So what it means is that basically, first of all, theoretically we'll see what it is, and then the physical significance I'll be asking you. Basically, here what we have is the zero frequency value. So zero frequency means this is the frequency scale axis over here. I think I've written over there, but it's partially hidden. This is the frequency axis in radians per second, okay, this side. And the other axis, of course, magnitude in decibels. You can see the three plots, it's written, labeled. Now, the zero frequency value means at a very low frequency, what is the value of magnitude? So here you can see in decibels, the value of the magnitude at zero frequency or very low frequency is equal to 0 dB. Over here also it is 0 dB, here also it is 0 dB for the system that we have taken. It's not going to be 0 dB for any system, of course. It is 0 dB for the system that we have taken. So now, basically, as per the definition of bandwidth, we have to find where the value of magnitude is minus 3 dB down from its zero frequency value, which means that in this case, since the zero frequency value is also 0 decibels, basically the frequency at which the value of the magnitude becomes minus 3 decibels or almost minus 3 decibels, that frequency will give us the bandwidth. So for the first plot, you find that here, the cursor is showing you minus 3.02. That is the closest I could get to the minus 3 dB value. So the frequency can be read from here, this plot So 0.641 radians per second. Similarly, for the second plot, again around minus 3 dB, the frequency has been read, and for the third one, third plot also around minus 3 dB, the value of the frequency has been taken. Of course, over here, this the second plot is sort of counterintuitive. It is, close to the frequency in this case, but it's counterintuitive. But as the value of your TP becomes larger and larger, you would find that the value of the frequency over here at which the minus 3 dB comes, the value appears, is going to become lower and lower. So now coming back to where we started from, the value of the frequency at which the magnitude drops to minus 3 decibels, which corresponds to 70.7% of the zero frequency value. That value of frequency gives you the bandwidth. But what is so special about that? Why do we, try to bother about the bandwidth at all? Can anybody tell me? What happens? What does the bandwidth physically imply? Why is it important? Any idea? You've studied it in filters, you said? What does this plot, the frequency response, actually show you at all? What is the physical significance of such plots? Magnitude versus frequency, what does it mean?
That means the system allows some frequency components to pass through it, and it rejects the other frequencies.
Yes, good. It's, more or less close. So here what we find is that, say for example over here, the value is equal to 0 decibels. 0 decibels means what? Any, signal of, say, whatever frequency this is, okay, 10 to the power minus 1, 0.1 radians per second, frequencies 0.1 radians per second or below that, they are going to pass through the system as it is, without any amplification, without any attenuation, because the amplification over here is equal to 0 dB. 0 dB means unity value. Log to the base 10 of 1 is equal to 0 dB. That is why 20 log, of course. So that is why basically in this range you can see the value is 0 dB means what? These signals of rather signals having frequencies which correspond to these values are going to pass through the system without any amplification or attenuation. The amplitude is going to remain exactly the same. On the other hand, say for example a signal which has a frequency of, this is 10 to the power 0, okay, 10 to the power 0, that is 1 radian per second, right? So any signal which has a frequency of 1 radians per second, now you find that the magnitude over here is much lesser than the 0 dB. It is around, how much is it? Minus 7 dB or something like that. So now, it would mean that signals having a frequency of 1 radian per second would be attenuated by that much amount when it passes, when it is applied to the system. So what this bandwidth means is that any signal which has a strength lesser than 7 or rather which is not a strength, which has a frequency such that attenuation occurs, and you find that the output is lesser than 70% of the original signal, those we assume are suppressed or attenuated sufficiently. So basically the bandwidth would indicate, that signals beyond that, signals having frequency beyond that particular frequency are going to be attenuated sufficiently, right? So that is what this bandwidth indicates. So now, say for this first system, means this for TP equal to 0, we had the bandwidth as 0.6, and for TP equal to 5, we had the bandwidth of 0.4. So that means that for the system without the additional pole, the bandwidth was larger compared to when the additional pole was added. Okay, so basically now if the value of this TP is increased further, we would find that the bandwidth would keep on decreasing. So that would mean that, I mean, signals having frequencies beyond this bandwidth are going to be attenuated. So over here for this system, signals beyond 0.4 radians per second are going to be attenuated, whereas for this system, signals beyond 0.4 are still going to pass through, whereas signals only beyond 0.6 are going to be attenuated, right? So that is, I mean, what is implied when we say that the bandwidth is reduced while when the additional pole is added. And reduction of bandwidth means that it cuts out high frequency components of the input signals, right? So basically, this is a general effect. This is also a general effect, reduction of bandwidth, general effect of addition of one pole to the open loop transfer function. Right. So now, I mean, coming to the next in the series, we have the effect of addition of one pole to the closed loop transfer function. So the closed loop transfer function was already omega n square by s square plus 2 zeta omega n s plus omega n square. So directly to that, one pole has been added, and the pole location is again -1 by TP. Of course, over here, this is a different system that we are studying with a different TP value maybe. So here now for this system, again, typical plots have been done. Typical plots have been done for here I think omega n equal to 1, that is the numerical value that has been considered. These are general plots just for the MATLAB, I mean, response. Some values were taken, that is what I mean you are seeing over here as values, indicated as values. So and a damping ratio of 0.5. So here it's going to be underdamped. You can understand the blue plot is for TP equal to 0. On the other hand, when TP equal to 1, you find the green response is the one that is, the plot for the response. And when TP is increased further, this is the plot for the response. And these are actually general trends. So if TP is increased further, you would find that the plot is going to even go, it's going to be more like an overdamped response. It's going to look like an overdamped response, right? So the general effects of addition of poles to the closed loop transfer function are, number one, reduction in the maximum overshoot of the closed loop systems. So basically you find that without the additional pole to the closed loop transfer function, this was the response, whereas addition of the pole has made the maximum overshoot decrease, and increasing the value has decreased it still further, right? Similarly, the second thing that you note over here is that it increases the rise time of the step response. That is evident. The response has become slower. And also reduction in the bandwidth of the system, thus cutting out high frequency component of the input signal. Here I have not done a separate plot for it, but you can understand what I mean. It's, I mean, sort of going to be similar to having a same trend is what I mean to the plot that I showed you earlier. Of course, that case is different, this case is different, but I mean, as far as the trend is concerned, the plots are going to indicate a similar sort of nature. So when one pole is added to the closed loop transfer function, the bandwidth reduces, and bandwidth reduces means it cuts off high frequency component of the input signals. The next, the third in that series is basically addition of a 0 to the closed loop transfer function. So here the closed loop transfer function was omega n square by s square plus 2 zeta omega n s plus omega n square, that you can see over here. With that, 1 0 has been added as 1 plus tzs, right? So now what is done is the responses have been compared and the general effects are studied. So here now, in this transfer function, this can be actually broken up into two parts as it is, isn't it? The first part being omega n square by this, and the second part being plus tz omega n square s by the denominator, right? So here now, if we are taking the time response would consist of two parts. One being the response due to this, the Laplace inverse of this part, which is going to be exactly similar to the second order response. This is going to be the same one. The second part is going to come from this second term, that is tz into omega n square s by the denominator, right? So now tz omega n square, of course, is a constant. What does this term s indicate? What is I mean, if you take the Laplace inverse, what would it indicate?
Derivative.
Derivative, yes. So you find that in this Tz is there, and then the original transfer function, the second order transfer function, omega n square by s square plus 2 zeta omega n s plus omega n square is already there, and then with that one s is multiplied. So it means that if you take the Laplace inverse, you would land up with this, that is Tz into derivative of this, that is C1, if C1t is the notation we use for the standard second order time response, that for this particular slide, then we have C1t, which is the Laplace inverse of this, plus Tz into derivative of C1t. This is the time response, right? So now if that were to be plotted by using MATLAB, that has been done over here with typical values, as I told you again. For specifically for this plot, omega n is taken as 1, damping ratio is taken as 1 as well. Now there is a specific reason why damping ratio is taken as 1. Damping ratio 1 means what? It's a critically damped case. So for Tz equal to 0, you would see the blue plot, that is the critically damped case. On the other hand, we find that there is the arrow has been misplaced a bit. This is the middle one, is Tz equal to 3, not this one, and Tz equal to 10 is the red one. So here now we find that though it is a critically damped case, that is zeta equal to 1, by addition of 1 0 to that second order system, which is critically damped, what has happened is that the response has become peaky. You find that there is an overshoot that is evident. So basically, I mean, that is the effect of addition of a 0 to the closed loop transfer function. So the general effect is increases the maximum overshoot of the closed loop system. Also, we find that the system response has become faster, as is evident from the green plot and the red one. Again, I repeat, the green one is Tz equal to 3, and the other one, that is red one, is Tz equal to 10. So decrease in the rise time of the step response. So these are general effects that would be observed when you have the addition of 1 0 to the closed loop transfer function. The next one in this series of actually 4, but there is a 5th case which I'll speak before winding up today. So addition of a 0 to the open loop transfer function. So here we have the standard second order open loop transfer function. The first one that we did was an open loop transfer function. So the transfer function was omega n square by s square plus 2 zeta omega n. That is the open loop transfer function. With that, a 0 has been added. So in order to study the effects, the closed loop transfer function corresponding to that has been calculated as gs by 1 plus gs, and this is what has resulted. So now you can see the transfer function and we can conclude certain things. So if the 0 were not added to the open loop transfer function, what would we have as the closed loop transfer function? The closed loop transfer function of the standard second order system would have been omega n square by s square plus 2 zeta omega n s plus omega n square. So with that, because of the addition of the 0, the closed loop transfer function has now become this. So what are the effects? I mean, what are the sort of characteristics that you see in this transfer function? The first thing that is visible is that the standard second order transfer function has the denominator as s square plus 2 zeta omega n s plus omega n square. Here an additional term in the form of Tz omega n square s has been added, and because it is a first order term, naturally it gives an added damping. It is actually going to increase the damping over here for the system, right? So increase in the damping means what? The response would become, say for example, if there was a maximum overshoot, increase in the damping would decrease the maximum overshoot, isn't it? So the system response would become more damped because of the increase in the damping over here, right? On the other hand, we also see another thing has occurred in this particular transfer function, that is in the numerator there is an added term, that is an additional 0 has come in the here. So that would imply that just previous to this we studied that, I mean, adding a 0 to the closed loop transfer function would increase the maximum overshoot. So that would mean that in this case, that is additional of a 0 to the open loop transfer function, there are two contradicting effects that we are observing. One is that of increase in the damping, which would decrease the maximum overshoot. The other is that of addition of a 0, which would increase the maximum overshoot. So in this particular case, the plot would have to be done based on the values. Which one is going to overpower the other is going to depend on the values, relative value of tz and these zeta omega n. But what can be said at least is that the overall plot would be a compromise or trade-off between these two contradictory effects, one of increase in the overshoot because of the 0, one of decrease in the overshoot because of the increase in the damping. So the general effect means is summarized over here. 0 increases the maximum overshoot of the closed loop system, but the term tz in the denominator has the effect of improving the damping, that is reducing the maximum overshoot. So here in this case, the plot has not been shown. It is, I mean, qualitatively, you cannot say whether the damping is going to be, whether the overshoot is going to be more or less. It is going to specifically depend on the relative values in this particular case. And which, I mean, if the effect of the 0 overpowers the effect of damping, then there will be a slightly greater overshoot. On the other hand, if the effect of damping is more compared to the effect of the increase in the overshoot, then the response would be slightly more damped, meaning lesser overshoot. So, okay. Do we have another 10 minutes or so? I hope so. So I'll just continue and finish up with this. So the system responses with additional poles. Here now we are considering for a second order underdamped case, the complex conjugate pole pair is placed at minus zeta omega n plus minus j omega n root over 1 minus zeta square. That's the general location of the complex conjugate pole pair. We've already done that. So now if we assume that an additional pole is added, that is one real pole at minus alpha r, then what is the effect? So first of all, I mean, the overall expression after, I mean, considering the additional real pole in the transfer function and then applying a unit step input, it has been broken up into partial fractions like this one, and then the Laplace inverse has been taken. So here what we find in the general time response expression for time response is that we have, first of all, this portion, if you recognize, it is the first portion of the response arising out of the step function that has been added. Step input gives rise to this first portion of the expression, right? First expression over here, I mean. The second one you see is an exponential, envelope with a sinusoidal term. You can combine these into a single sinusoid. So basically a sinusoidal term with an exponential envelope is what you have in the second term. The third one is the added one, where we find a constant into e to the power of minus alpha r t. So now if you recognize, this minus alpha r is the pole that we had placed. And now you can understand that depending on the value of alpha r, meaning whether if alpha r is close to the imaginary axis, meaning it has a small value, what will happen? If it has a large value, meaning it is pushed to the left half, or further towards the left, that is, it has a large value, what will happen? Those can be studied. So now can you tell me, okay, for a specific complex conjugate pole pair with this particular placement, let us assume that this real part of the pole, that additional pole is say very small compared to the real part of this complex conjugate pole pair. So very small means what? This minus alpha r that we have over here, the value is small. Small means what? Will it decay faster or slower? The value
Slower.
of, yes, it will decay slower, meaning it is going to have the effect of this added pole will persist for a larger amount of time. Okay, so the effect will be visible. on for a larger amount of time. On the other hand, if this real pole value was very large, okay, large means very large means compared to the real part of this, say it is 10 times of that. Okay, so if say for example minus zeta omega n is minus 1 plus minus j something something, then this is at minus 20 or something. So that is large compared to the real part of this. So relative values are what I'm speaking of. So if the real part over here is large compared to this the real part of the complex conjugate pole pair, what will happen? Naturally this is going to decay much faster, meaning that the effect of that additional pole is going to be persisting for a smaller amount of time. Okay, what we can say is that if this real pole were pushed farther and farther to the left such that it goes to almost minus infinity, then this effect would be almost equal to very negligible, that is, isn't it? So basically, that would be equivalent to having only the complex conjugate pole pair without the real pole. So that is what we are going to see. I think the plots are given over here. Yes. So okay, so the complex conjugate pole pair has been placed. Real part is minus zeta omega n. You can see that imaginary parts are shown. Now minus alpha r is the real pole. So case 1 is alpha not much larger than zeta omega n. So it's comparable. So comparable means both the effect of both the terms meaning the second and the third term, both of them have to be considered. Right, I told you about the extreme cases, in which case we are going to visualize, we would be able to visualize to a much greater extent easily. So now if alpha r is much larger than zeta omega n, so alpha r larger means it's far to the left. So that means that the effect of that pole is going to be smaller. So case 2 you can see is this green one over here, and then case 3 is alpha r equal to infinity, basically. So the pole is at minus infinity. So the third one is what you have. This is the plot for minus infinity. So basically alpha r equal to infinity, So now let me say something I missed out there. That is, here the plots have been done with a damping ratio of 0.7. So 0.7, what sort of response do we expect? We expect an underdamped response. Underdamped means it is going to be slightly oscillatory before it reaches the steady state. So the third one is actually the response that is corresponding to the underdamped response, which is also going to be the same when alpha r is equal to infinity, meaning that this pole is at minus infinity. Okay, so only the effect of the complex conjugate pole pair and the response thereof would be visible as case 3 over here, the pink one. Okay, on the other hand, when this alpha r is large but not negligible, then we would see that the response is a bit different from the one that we had earlier. Different in the sense that basically it is going to be getting closer to the exponential sort of response. Of course, we still see the effect of the second order pole pair, as well as the effect of the additional pole. And for case 1, alpha r is not much larger than zeta omega n, in which case we find this is the case, right? So now yes, so a case may have arisen in which case, say for example, this, it's not given on the slide, but tell me whether you can understand. Let us say that the complex conjugate pole pair is here. Now let us say that the complex conjugate pole pair is pushed far to the left hand side, such that the real part of the complex conjugate pole pair becomes much larger compared to the alpha r value. So then what will happen? If you look at the expression over here, I'll repeat what I said. I said that your complex conjugate pole pair, this real part is much larger compared to the real pole value. So now what will happen? From the time response expression, can you say what will happen if real part over here becomes much larger compared to minus alpha, I mean.
Sinusoidal part will be negligible.
Yes, the sinusoidal portion, the envelope of the sinusoid will decay very fast. So that, I mean, it's going to start off, but it's going to, I mean, be damped out very fast, so that the effect of the sinusoid will almost not be visible in the response. The response will consist of purely this first term and the third term. That is, it's going to appear as if it is almost an exponential response only, because the sinusoidal term, though present over there, will be damped out very, very fast. So you can now, I mean, qualitatively understand what will happen, I mean, if a real pole is added, and also, I mean, the dependence, or rather the relation between the real pole magnitudes of the real pole and the real part of the complex conjugate pole pair. The effect of the relative values is going to be evident in the response, right? Which one is larger is going to indicate whether I have a response close to the, which is going to look almost like an exponential response, or whether it's going to look like almost the second order sinusoidal response, or whether it's going to be midway in, somewhere in between, I mean. Okay, so that was the additionally. I think this is dominant touch. I wish I could finish till the end of that. Let me see. Okay, so now we come to something which is known as non-minimum phase zero. So it is like this, that is, if you have a zero which is in the right half of the S-plane, of course, I mean, if you have a pole to the right half of the S-plane, the system becomes unstable, isn't it? But if you have a zero to the right half of the S-plane, the system response does not become unstable. On the other hand, of course, there is going to be some effect on the overall time response. So, excuse me, here we are going to study what that effect is going to be. So here, to the closed loop transfer function, standard closed loop transfer function of a second order system, a non-minimum phase 0 has been added, where the zero location, as you can see, is at plus 1 by tz, right? So that now, I mean, if we break it up into two parts, first is omega n square by this, and the second one is minus tz omega n square s by this, right? So now if we try to see what the time response is going to be, time response will be the second order time response, if we denote as c1t, minus tz into, now again we have s into omega n square by this. So it's going to be a derivative of the second order response multiplied by tz. Because of the negative sign, there will be a negative sign over here. So the overall time response is going to be equal to the second order response minus some constant value into derivative of the second order response, right? So now if we do that plot for a typical set of values, say for a critically damped case, we are doing it just to visualize. So omega n equal to 1 and tz equal, zeta equal to 1 as well for the critically damped case. For tz equal to 0, the blue plot, that is the critically damped case. So now if tz is equal to some other non-zero value equal to 1, say for example, then we will have the response as the second order response minus something. So you can see that the response actually is, I mean, the for each instant of time, the response value is going to be this value minus some quantity. That is what you see in the green response. Similarly, if the tz value is increased far, I mean, a bit more, to tz equal to 2, you find that this red one is the response. So basically, because of the addition of the non-minimum phase 0, what has happened is that this is the zero value, zero amplitude. The response has gone to the negative side and then, I mean, started rising. Here also you find that it has gone to the negative side and then started rising. So this is something that we call as the negative kick in the response. So the non-minimum phase 0 essentially introduces a negative kick in the response. So basically, if you have a time response given to you and you find that it has gone to the negative side before rising to the positive side, you can just close your eyes and you can say that, oh, there must be a non-minimum phase 0. I mean, there is a high chance of occurrence of a non-minimum phase 0 if you observe such a response. That is, a response which has a negative kick before going to the positive side, right? So that is the effect of a non-minimum phase 0. So I have just one small portion to cover before I finish off for the day. That is the concept of dominant poles. Now, till now, I've just before this, told you about the effect of addition of one pole to the second order transfunction, etc. And I've told you that, okay, relative to the complex conjugate pole pair real part, the real pole value is larger. Now, how large is larger and how small, is small, that is something which is relative. So that is what is dealt with over here. Now, the location of the poles of the transfer function have great effect on the transient response of the system that we've seen. For analysis and design purposes, it is important to sort out the poles that have a dominant effect on the transient response and call these the dominant poles. So we may find that basically, there are some poles which have a much larger effect or significant effect on the system response, and some other poles which have minor effect on the system response. So the poles which have much larger effect on the system response are called dominant poles. Now, till so far we've already seen that poles which are closer to the imaginary axis are actually going to have a much the response is going to persist for a larger period, meaning that the effect on the response will be much larger or more significant compared to poles which are far apart. So here there is a segregation of the two regions. One region is denoted as region of dominant poles, the other is written as region of insignificant poles, and there is a you can see there's a distance which has been marked as d over here. Now, there is no absolute value that you can say, okay, a difference of 10 over here is going to tell you that these are insignificant poles and those are dominant poles. No, basically this is a relative thing. So how far or how close compared to the dominant poles is what matters. I'll go to the next slide and tell you what exactly typically we would be considering. So here now in this you can see the S-plane, the region of the dominant poles. If you have a complex conjugate pole pair around 45-degree angle over here would give you region of dominant poles over here. On the other hand, is that so okay, so I'll just finish off in say 3-4 minutes if you have a class anyway. So basically this portion is the region of insignificant poles, and there is a difference distance between the two given as capital D. Now, how much is that? That is going to be stated. As I told you, it's a relative thing, and absolute values are not possible. I'll be doing it in a subsequent slide. Now, in design, we can use the dominant poles to control the dynamic performance of the system, because the dominant poles are what dictate how the response is going to be like. Now, the insignificant poles, then why do we require the insignificant poles? The insignificant poles are used for the purpose of ensuring that the controller transfer function is realizable. It can be realized by using physical components. So everything is not mathematical in nature. So basically, say for example, if you have the requirement of say placement of 2 zeros, so naturally now to balance that you may have to place some insignificant poles somewhere which are not going to have a sufficient significant effect on the response itself, but nevertheless it is going to make the system realizable, meaning you can realize the system by using physical components. The poles that are close to the imaginary axis in the left half of the S-plane give rise to transient responses that will decay relatively slowly, whereas poles that are far away correspond to fast decaying time responses that I've already spoken. Just one slide somewhere, which in practice, if the magnitude of the real pole is at least 5 to 10 times that of the dominant pole or pole pair, complex conjugate pole pair, then the pole may be regarded as insignificant. So if the dominant poles are at say minus 0.1 plus minus j2, something like that, then a pole at minus 1 is 10 times far away from that. and can be considered as an insignificant pole, right? On the other hand, if we have the complex conjugate pole where at minus, say 0.9 plus minus j something, then a pole at -1 is going, you cannot consider that as an insignificant pole. That also will, I mean, be a dominant pole. So around 5 to 10 times of the dominant pole would be considered, if in magnitude, would be considered as the insignificant poles. For design purposes, such as in pole placement design, the dominant poles and insignificant poles are selected by the designer, and sort of it is desirable that they be placed as shown over here. That is, you have complex conjugate pole pair, then these are the locations which will give you a desired damping ratio, not more than that, not less than that, and the insignificant poles are placed around 5 to 10 times away from that in these regions. I think that is, yes. So this, I think, is the last slide. The same, information over here. This also is a repetition. One more thing, relative damping ratio. Now, in systems which are higher ordered, higher than second order, what is done is that these systems are basically sort of approximated by a second order system, and then the damping ratio of such a second order system, which is replacing the original higher order system, that damping ratio is called the relative damping ratio. So for higher order systems, the damping ratio and the undamped natural frequency are no longer used, as they are defined for only a second order system. However, if the system dynamics are accurately represented by a pair of dominant poles, then we can still use zeta and omega n to indicate the location of the poles. And in this case, the damping ratio is referred to as the relative damping ratio of the system. So it is essentially the damping ratio of a second order system, which is replacing a higher order system. The response is similar to the higher order system, but it is, the higher order system, because we cannot analyze or design, basically it is being replaced by a smaller order second order system. The damping ratio of such a second order system is known as the relative damping ratio. So that is all that I would be stating over here in today's class. If you do have queries, we'll address that